Hi everyone. So today we're going to talk about impulse and momentum. So first, impulse and momentum has to do with collision. So collision is just a short duration interaction between objects. So collisions are basically when objects hit each other. They're not actually instantaneous. They do take time, even if it's some very, very small amount of time. How long this duration of the collision is usually depends on the material, right? How flexible it is, so to speak. But generally speaking, 1 to 10 milliseconds is a typical time for a collision. So the harder the object is, the shorter the contact time. So in physics, we like to study this, these collisions and interactions between objects, right? So we have a name for the force exerted on an object for a certain amount of time. We call that impulse. So specifically, it's the area of a force versus time graph. This is generally impulse we're dealing with short amount of times. So if we have a large force applied for a longer amount of time, we're going to have a larger impulse. Okay? So here we have a force versus time graph. You see here that this force is non-constant. So when an object hits another object, right, if you can imagine a ball hitting a wall, it's going to go press a bit, right? And so it's going to be a non-constant force when it does that compression. And the point of maximum compression of the object is going to be the peak of this graph, where it has a maximum amount of force acting on it or it exerting on the other object. And then it's going to bounce back, and so we have this impulse shape. These impulse graphs can be complex in shape. Generally, they're going to have a bell-type curve to them. But in this class, we cannot calculate the area underneath a curve. So what we're going to do is very often we're going to either have impulse graphs that are triangles, so it's easy to find the area under that triangle, or we're going to use the average force exerted over a certain amount of time. And so we're going to define impulse. Often impulse is symbolized with the capital J, and that's going to be average force multiplied by the time that force is exerted. Okay. Impulse is a vector quantity because average force is a vector quantity. It has units. Since we're dealing with force multiplied by time, that's newtons times seconds. But preferably we write that as kilograms times meters per second, and I'll talk about why that is later. So a quick question here. So let's suppose we have a tennis ball and a racket, and they collide, right? So we're hitting a tennis ball with a racket. Here is the impulse graph, or the force versus time graph for this tennis ball. What is the impulse that ball experiences, right? And then we want to draw a force versus time graph for the racket. So please take a moment, think about this, and then unpause. All right. So we can calculate the impulse with the area under this graph, right? So since we have a triangle, we can do half the base times the height, right? And that gives us 0.9 kilograms times meters squared. So that is the impulse of this collision. Now, the force of the racket on the ball and the ball on the racket, that's a Newton third law pair, right? So the graph's going to have the same shape as the graph we have here, but it's going to be negative, right? So I don't have that drawn, but you guys can figure that out. Right. So we can also quantify impulse in a different way, right? So when we're dealing with collisions, the effects on an object depends on the object's mass, right? So kicking a heavy object, it's going to change its velocity much less than a light object, right? So kind of thinking about inertia, kind of a thing we have going on. But we have another name for this. We're going to quantify this relationship as momentum, right? So momentum is we're going to symbolize it with a lowercase p because of the silent p of momentum. So impulse is the change in this quantity, this change in momentum. So momentum is just mass times velocity. Please note here that momentum is a vector because velocity is a vector, and they're going to point in the same direction. So the momentum of the object points in the same direction as that object's velocity. Right, and we can see here the units for momentum are going to be mass, kilograms, times velocity, meters per second. So kilograms times meters per second. And that's why this is the preferred unit for impulse, since impulse is the change in momentum. We also have something called the impulse momentum theorem, right? This is extremely important, almost as important as the work energy theorem, or actually equally as important. And this states that the change in momentum of an object is equal to the force of that object during the collision times the change in time, so the time of that collision. So this is just basically saying that the impulse an object feels is going to cause that object's momentum to change. Now, it's going to be very common in these types of problems to deal with this in component form. So if we have some sort of force acting on an object that happens to be at an angle, right, during this collision happens at an angle, we're going to have to break this up into components so that the change in momentum in the x direction of your system is going to be the force in the x direction times the time of that collision, and we have the same thing for the y direction. So here we're dealing with just a one-dimensional situation. We want to calculate the change in momentum of this ball. So we have a ball of mass 20.25 kilograms, and it's rolling to the right at 1.3 meters per second. It hits the wall, rebounds to the left at 1.1 meters per second. What is the change in this ball's momentum? What is the impulse delivered to it by the wall? So take a moment, write down what you know from this problem, draw a diagram if you'd like, and then I'll talk about how we can solve this problem here. So hopefully when you're defining these quantities, so you wrote down mass. I don't know why that capitalized. I guess it auto-capitalized. That's 0.25 kilograms. Our initial velocity, I'm going to call to the right being positive here. So our initial velocity is 1.3 meters per second. And that makes our final velocity negative 1.1 meters per second because our ball is now going to be moving to the left after it hits the wall. So that's going to be a negative quantity. So let's see. What is the impulse delivered to it by the wall? We want to calculate impulse. So impulse is change in momentum, right? So that's our final momentum minus our initial momentum. So I'm going through that here, plug in the numbers, and we get negative 0.6 kilograms times meters per second. And based on my coordinate system, so to define the right as being positive, a negative impulse is meaning that it has an impulse of 0.6 kilograms times meters per second to the left. We can also have more than one momenta going on in a system, right? So if we define our system to be a couple billiard balls or whatever situation we have going on, it can be more than one object. And the total momentum of that system is just going to be the momentum of each object in the system added together. And this is the vector sum of these quantities. So kind of changing gears here, or kind of reviewing, I should say. So take a moment and pause to think about this question. Come up with an answer and we'll discuss it. All right, so looking at this here, the whole point of this, we're trying to find which has a greater final speed. Well, we know that impulses change in momentum, right? Both of these cue balls are initially at rest, right? So basically, whichever one has the larger impulse is going to have the larger final velocity. If you're looking at these graphs, impulse is just the area under these curves, well, these rectangles here. And if you look here, the areas are actually equal to each other, so they're going to both have the same final speed. All right, looking at another example here, so let's suppose we have a 150-gram baseball. So we're probably going to have to change that to kilograms. And it's thrown with a speed of 20 meters per second. It is hit straight back towards the pitcher at a speed of 40 meters per second. The impulsive force of the bat on the ball has the shape shown. We're first asked what is the maximum force that the ball exerts on the bat exerts on the ball, and what is the average force that the bat exerts on the ball. All right. And both those values, I'm going to calculate the magnitude of that force. All right. So we see here we have an impulse graph here. We have some sort of maximum force value. We don't know what that is. And oh, it got cut off. I'm really sorry about that. But the length here of this impulse is 0.6 milliseconds. All right, I'm sorry my screen kind of cut that off, but 0.6 milliseconds is the duration of this impulsive force. So kind of drawing a diagram of this situation, I'm going to assume initially the ball is moving to the left. This ball has a mass of 0.15 kilograms and it's moving at negative 20 meters per second. After our collision, right, our ball is now moving to the right at 40 meters per second. Now, in order to calculate the maximum force, right, we know the area under our graph is the impulse, not in the impulse, is the impulse, the change in momentum, right? So basically we're going to use the information we gather from this graph here. Well, so impulse, J, is change in momentum. And impulse, based on this graph, since we have a triangle shape, it's going to be 1/2 base times height. Right? So it's 1/2 my height being F max, and my base being this 0.6 milliseconds that you can't see that's supposedly labeled. And that's going to be equal to my change in momentum, right? Where my change in momentum is mass times my change in final change in velocity. All right, so rearranging this, solving for F max, we have this expression down below, plug in our numbers, and we see that's 30,000 newtons. All right, so that's the maximum force that this ball experiences. So when the ball is hitting the bat, at its point of maximum compression, that's the force it feels. Okay. But we can also calculate the average force that this ball feels. Since when the ball hits the bat, it's going to feel a variety of forces. So what is that average value? Right? Again, we're going to use the impulse momentum theorem. But this time, we're going to use this approximation for impulse. That's going to be the average force times time. Right? I kind of mentioned that on one of the first slides. Right? So the average force times the time which that average force is exerted is going to be the change in momentum. Right? So our average force here, we rearrange solve for that. We see that the expression we get is the same expression as before, but half the value. So we're going to get half of 30,000 newtons, which is 15,000 newtons. We have also something called the impulse approximation, right? I think you guys are going to like this because it means we have to worry about less stuff. So when two objects are interacting with each other, when they collide, it's a very brief interaction, but when that brief interaction occurs, usually it's with very large forces. They're generally quite large. Right? What's really great about having a force be quite large is that when we compare it to other forces that are involved during a collision, so perhaps the gravitational force is going to be practically negligible compared to this impulsive force, this impulse force. So we call this the impulse approximation. That means that when we're calculating the force during a collision, we don't have to worry about these other forces because they're going to be too small to have to worry about. Right? And just also to note, when we're dealing with initial momentum and final momentum, the momentums that we deal with are immediately before and immediately after the collision, right? So not when the objects are in contact with each other. So one final question I have for you guys. I'm actually not going to answer this question. This will be due now next class. But let's suppose we have this 10-gram rubber ball and a 10-gram clay ball. They're each thrown at a wall with equal speeds. Okay? The rubber ball bounces and the clay ball sticks. Which ball receives the greater impulse from the wall? Have a great day, you guys. And I can't pause the play thing.